Universe, an 8-letter word. But this 8-letter word is everything around us, including us. Right from a phone that you're holding right now, your pen placed on your working desk, to the giant stars, galaxies and planets. All these things are part of the universe. This seems to be a really big thing. But how giant is the universe? In order to understand the size of the universe, we need to explore the types of the universe first. Normally, the universe is divided into two parts. The first is observable universe, and the second is unobservable universe. The observable universe is a spherical volume centered on the observer, regardless of its shape as a whole. Imagine yourself to be the center of a big ball. Now you are the observer, and the fraction of ball that you can see is the observable universe. And the rest which you cannot see is an unobservable universe. As we have seen the types of the universe, now it's time to disclose the real value of the size of the universe. The radius of the observable universe is 46 billion light years. In kilometers, it is equal to the number which is appearing in the screen. But the number has been incorrect. Since the universe is expanding in each fraction of time. But how is it incorrect? In order to understand that, first we need to understand the way of measuring the universe. Our way of measuring the universe is by the light itself. As we know that the light has the fastest velocity, that is equal to 1,86,000 miles per second. Isn't it too fast? It is absolutely fast. But the speed of the light is also a limitation for us for measuring the size of the universe. Because as long as the light reaches to our eyes, the universe is already being expanded. This makes it impossible for us to measure the exact size of the universe. However, there is always a hope. This hope could be temperature and density. The universe is cold and clumpy today, but it is also expanding and gravitating. As we see things at greater and greater distances, we see things as they were not only far away, but also back in time, moving to the finite speed of the light. The more distant universe is less clumpy and more uniform, having had less time to form larger, more complicated structures that require more time for gravity's effect to take place. The early distant universe was also hotter. The expanding universe causes all the light that travels through the universe to stretch in a wavelength. As the wavelength stretches, it loses energy, becoming cooler. This means the universe was hotter in the distant past, a fact we have confirmed through observations of distant features in the universe. We can measure the temperature of the universe as it is today, 13.8 billion years after the Big Bang, by looking at the leftover radiation from that hot, dense early state. Today this shows up in the microwave portion of the spectrum and is known as the cosmic microwave background. Coming in with a black body spectrum and temperature of 2.725 Kelvin, it is easy to confirm that this observation match with an incredible precision the predictions that arise from Big Bang model of our universe. Moreover, we know how this radiation evolves in energy as the universe expands. A photon's energy is directly proportional to the inverse of its wavelength. When the universe was half in its size, the photons from the Big Bang has doubled the energy, while when the universe was 10% of its current size, those photons had 10 times the energy. If we are willing to go back to when the universe was just 0.092% its present size, we'll find a universe that is 1089 times hotter than it's today, around 3000 Kelvin. At these temperatures, the universe is hot enough to ionize all the atoms in it. Instead of solid, liquid, or gas, all the matter in the entire universe was in the form of ionized plasma. From the full suite of observations available, including the cosmic microwave background but also including supernova data, large-scale structure surveys, and baryon acoustic oscillations, among others, we get our universe 13.8 billion years after the Big Bang. It's now 46.1 billion light years in radius. That is the limit of what is observable. Any farther than that, and even something moving at the speed of light, since the moment of the hot Big Bang will not have had sufficient time to reach us. As time goes on, the age and the size of the universe will increase. But there will always be a limit to what we can observe. So what can we say about the part of the universe that is beyond the limits of our observations? We can only make inferences based on the laws of physics as we know them, and the things we can measure within our observable universe. But this is not the end of the human's journey for the exploration of the universe. Human's journey to the universe will continue in the future, with more and more fascinating and thrilling consequences.